the new part of chapter 29. Unfortunately, I have recorded one and it was not saved. I have a problem with the storage on my iPad. Therefore, I'm gonna use my Mac to record. And in this one here, in a physics laboratory experiment, a coil with 200 turns enclosing an area of 12 cubic square centimeters is rotated in 0.040 seconds from a position where its plane is perpendicular to the Earth's magnetic field to a position where its plane is parallel to the field. The Earth magnetic field at the lab location is 6 × 10⁻⁵ Tesla. What is the total magnetic flux through the coil before it is rotated? And then after it is rotated, what is the average EMF induced in the coil? This is a very straightforward, I will say, question. And the first thing is I'm listing my knowns and unknowns. Then N is 200 turns, A is 12 × 10⁻⁴ meters squared, and T is 0.040 seconds. And theta I here, this is very important. If you look here, you are going to find that they said it's from the position where it's plane perpendicular to the Earth magnetic field. This means that when we are going to look at the surface area, at the area vector, is going to be aligned with B, because this is the plane, or it is perpendicular to the magnetic field of the Earth. And then now theta I is 0, and when it's gonna rotate and is gonna its plane is gonna be parallel to the field, then the angle is gonna be 90. Now theta I, it is in B a cosine 0, and then when I plugged my numbers, the flux is 1.44 × 10⁻⁵, and for theta 2 it is 0, and okay, I'm sorry, and then the change, it is okay, then the change, it is the change in delta phi. Okay, I'm not used to using it, therefore it's a little bit hard. Let me see. I'll get rid of this highlighter. Yeah. Then now here delta phi over delta t, it is 1.44 10⁻⁻⁵ Weber divided by 0.0405. Okay, this one, it is like, it should be negative here, but we have 0 minus, and then it's gonna get have this taken care of it. Okay, I'm gonna do a lot of this. Yes, okay, then I'm gonna use the scroll up and down. Okay, and then here I have the result. Okay, now I'm gonna move to the second one, where I have a flat rectangular coil of dimensions L and W, length and width, is pulled with uniform speed dV through a uniform magnetic field with the plane of its area perpendicular to the field as in the figure. Find the EMF induced in this coil if the speed and magnetic field are both tripled. What is the induced EMF? Now theta B is N times B a cosine phi, and I will say the EMF is going to be negative d phi of beta of B divided by delta t. The flux is constant in each case, then no change, no EMF, even if the magnetic field is tripled and the induced EMF. If the flux is constant, then there is no change and the flux, and I will say we are going to have 0 EMF. Here we have the current I in a long straight wire is constant and is directed toward the right as in the figure. Conducting loops A, B, C, and D are moving in the directions shown near the wire. For each loop is the direction of the induced current clockwise or counterclockwise, or is the induced current 0? For each loop, what is the direction of the net force that the wire exerts on the loop? Give your reasoning for each answer. This one, it is based on the rules that I posted, like originally I will say before Lenz's law here, these ones, okay? Okay, then this is really related to Faraday's law determining the direction of the coil of the induced EMF. Then I will go back to here. Now, the first thing I'm gonna do is I will find the direction of the magnetic field of the wire, and the current is going to the right, then I will say if we are going to use the right hand rule, you're gonna use for the current I your thumb, and you're gonna curl your hands and your fingers in the direction of the magnetic field. Then on top of the wire is gonna be out of the page and is gonna enter into the page below the current. I did here, this is for coil A. The magnetic field here at its position, it is out of the page. The motion V is upward, and then here we can say the flux, because it is moving away, is decreasing. Then B original is gonna be I will say out of the page, and B induced is gonna be out of the page as well, because there is a decrease in the magnetic flux. Therefore, again, using the right hand rule for the current, we are going to find that the current should be counterclockwise. You're gonna point your hands out of the page. I would say you're going to point your thumb out of the page, and your fingers, they're gonna curl counterclockwise. This is the direction of the current. For the second coil B, it is again I'm here drawing B. It has it is below the wire. Then it has also its motion moving away from the current or from the wire, the flux decreasing. Original, it is into the page, and then I will say induced is should be also into the page as well, and then the current should be clockwise. For C, it is not in motion. I will say it is not changing its distance with respect to the wire. It is moving like parallel to the direction of the current. Therefore, there is no induced current. For D, it is moving toward increase in flux, and therefore B original it is, and it is below the wire. Then it is cross. The induced should be into the page, and then the current should be counterclockwise. For each loop, what is the direction of for each loop, what is the direction of the net force that the wire exerts on the loop? We can do this in two methods. One of them is you're gonna say whenever the flux is increasing, the current, you can use the flux idea. Whenever the flux is increasing, then I will say the net is gonna be attraction. And okay, again, let me say that again. We are going to use the idea of the flux. Then whenever we have a flux that is really decreasing, is going to be attraction. And if it is going to be increase in flux, it should be repulsion. Again, let me repeat that again. I'm not focused, I'm so sorry, because what I'm going through now. Okay, I will say if we have a decrease in flux, then what we are going to have is going to be a net attraction. If we have an increase in flux, the net is going to be repulsion. Okay, what I like the other method, which is this is my wire and this is really the loop. These two currents, they're going to create forces that they are going to be in opposite directions. They're going to cancel. For these here, this one, it is this one, it is attraction because the direction are in the same direction. For this wire, it is gonna repulsion because opposite direction currents. Now the attraction is closer to the wire, then it is net attraction. For loop 2, what I can do is for loop 2 or loop B, for loop B, it is again a decrease in flux, therefore it should be net attraction. Okay, and for loop C, we don't have a current and no force. For loop D, it is an increase in flux, therefore is gonna be repulsion. Or again, use the same idea. 1 is repulsion, 2 is attraction. We have more repulsion than attraction, and therefore it's gonna be not, I will say, net repulsion. I said here also you can use the idea of flux. I did explain most of my solutions based on the forces between two parallel wires, but also you can use the other explanation. Thank you. I will do another video for this.